Good morning, everyone, and thank you very much for joining us for today's webinar, Effective Project Planning for Tall Timber Residential Build. My name is Claire Hepburn. I'm the Deputy Registrar at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we begin, I'd like to share some important information to ensure an effective and professional webinar experience. Please be informed that the session is being recorded for quality and educational purposes. To maintain a stable internet connection, we've muted all participant microphones and disabled video feeds. We would highly encourage engagement through our Q&A window. Feel free to submit any questions that you have for our speakers. These will be addressed in the designated Q&A period at the end of the presentation. Also note that the chat function will be deactivated following this introduction. And for those who are seeking continuing education learning hours, please note that your attendance is crucial. You will need to attend a minimum of 80% of this session to be accredited these hours onto your OAA transcript. And just allow a couple of weeks to process and report these hours. Lastly, please note that our presenters today do not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. For accessibility, we provide automated closed captioning services available in multiple languages to accommodate the needs of our diverse audience. And now I'm excited to introduce our speakers for today's session. Please welcome Ilana, Danzig, and Amir, Shahrokhi.
Thank you so much, Claire.
Over to you.
All right. Hi, everybody. I'm thrilled to be here. My name is Ilana Danzig, and I'm a structural engineer and managing principal at the Vancouver office of Aspect Structural Engineers. Over my career, I've worked on a wide range of project typologies with a focus on offsite prefabrication and mass timber construction. I'm engineer of record for a number of mass timber or hybrid multifamily residential projects throughout Canada and the United States. And I was on the team for Tallwood 1 on the West Coast, which is Canada's first EMTC encapsulated mass timber construction building. And I'm pretty excited to be sharing my experience and learnings with you today. And I'll pass it on to Amir to introduce himself.
Thanks, Ilana. Hi, everyone. Amir Shahrokhi. I'm Associate Principal in our Toronto office. I also serve as our Director of Innovation. I've also have similar experience with mass timber buildings as Ilana, and started my career as an architect in New York and worked on some of the first tall timber buildings there that were sponsored by USDA grants, and have continued on that trajectory here as well.
So at Aspect, we're a structural engineering firm at heart, but we have multiple service offerings. We provide structural engineering across all project types and all materials. But for mass timber specialty services and fabrication design, we specialize in those areas, providing mass timber services. Our experience is broad. Here is shown some of our mass timber experience specifically, which includes recreational, student housing, multi-unit residential as well. And today we'll be talking about tall wood and why to use tall wood. We'll be talking about some of the mass timber code changes and the new EMTC requirements. We'll do a deep dive into tall timber project timelines and how tall timber project process works. And then we'll leave you with a few things to take away for your own projects or your own work.
So I'll start us off. I think it's always good to ask ourselves why we're talking about wood in the first place, and remind ourselves of why the bigger picture, and not just the code requirements and some of the changes that have occurred recently. So I'll do a little bit of a zoom out, and then we'll get to the heart of the presentation after that. One of the key factors in talking about wood in construction is actually urbanization, and I think we're all familiar that the trend has been that we're in an increasingly urbanized world, and we reached the tipping point in about 2007 where urban populations have surpassed rural populations, and that's continuing to be projected to grow. And so, we need to house everyone, and we need to do it in a way that is sustainable for our future. Similarly, I think everybody's probably familiar with this by now, but the building sector is responsible for about 40% of greenhouse gas emissions. Now, that's both embodied carbon and operational as well. And that falls on us as building professionals to control how we responsibly build these buildings in a way that is responsible for the future. So if we compare our sector, the construction sector, to others, if we take into account both the operations as well as the materials that go into them, like we looked at in the previous slide, it's about 40%. And that is, by far greater than things that get a lot more attention, like transport and industry. And then when we zoom in on buildings, and break down the subcomponents of buildings, you'll see that superstructure and the substructure compose more than half of those of that embodied carbon, and then that's followed by things like the cladding, and then the M&E and the transport that goes into getting the materials to site. But the superstructure and substructure are by far the greatest components of the embodied carbon in a building. So what are our options in terms of reducing the carbon in buildings? So we can build nothing, but that's not, as we started off, we need to build more, not less, if we're going to provide shelter for everybody. So that's not usually an option, but we can think about the stock that we already have and adaptively reusing that. So that's the least invasive option that we have. The second is to look closely at what it is that we're planning to build, and deciding whether it's essential or not, and really honing in on building only what is essential. And then once we're past that, then we've got the scheme. It's as essential as it could be. Then it's about what goes into it, right? So the smart choices in terms of materials, and the specifications in terms of keeping the emissions low. And then lastly is the operational part. So having systems that operate as efficiently as possible to reduce the ongoing operations. So when we look at a comparable building of 12 stories in concrete superstructure versus a mass timber, we can expect at least a 30% reduction in the embodied carbon in the timber version. And then breaking that down even further into the subcomponents, well, where does that come from? So foundations, we don't see a significant savings because that's still going to be done in concrete, but we see some reductions due to the lighter weight of the timber building out that it's supporting. But the majority of that comes in the walls, the floors, and the roofs. So in general, timber is a material that's sequestering carbon throughout its life and storing that within its fiber, versus steel and concrete, are energy intensive to produce and emit a lot of carbon through that process. The other factor is the way we built. So the typologies that we use. So historically, in the latter half of the last century, there was a lot of single-family homes that were built rather than multifamily, denser typologies. And by shifting more towards denser typologies, we also see a reduction in both operational and embodied carbon. And a quick case study on that about the sequestration potential of building in timber and looking at various densities of construction. So if we take a suburban typology on the left versus an urban one on the right and various in-betweens, we see almost a 10-fold increase in the carbon sequestration potential if all of those things were to have been built out of timber. And then the lastly, to kind of wrap things up, there is what we call this virtuous cycle potential when we build more in timber by taking the raw materials that we have in rural areas, the trees and forests, and creating value-added materials out of those that help us build sustainably our cities. And then those economic benefits flow back to those rural communities. And so they are able to raise their standards of living and keep reinvesting into sustainable forestry practices, and then creating further value-added goods and perpetuating this virtuous cycle. And then there are a whole host of other benefits in terms of working with timber and construction, some of which are laid out here. We covered predominantly the carbon benefits, but the cost-wise, the timber buildings are coming in quite competitively with steel and concrete when you take in the schedule savings. And that reduction in construction time leads to income coming in more quickly from the buildings, and they are less disruptive due to the reduced on-site activity and safer working conditions, because there's just less folks on sites, and because a lot of it is done off-site, you have higher quality and tighter tolerances in the construction of those materials.
Okay, thanks, Amir. I'll talk about some of the timber components and where we are with tall timber today. Next slide. Yeah. So to start with, we have a timber family tree, and the idea here is that all of the wood products that we use can sort of be traced back to the log in different ways. So we have the log that gets harvested. That can either turn into heavy timber or dimensional lumber on the left, or veneer lumber or wood strands. And then each of those forms the products that we see in mass timber today. So glulam, naillam, CLT are from dimensional lumber. Laminated veneer lumber, LVL, and mass plywood panel, MPP, are from veneer lumber. And then we get PSL and LSL from wood strands. Tall timber is not new. In fact, it's been built for hundreds of years with lots of examples of well-preserved, well-maintained structures from long ago. So we have temple examples from hundreds of years ago that are still in good shape. We also more recently, at the turn of the last century, saw a lot of the brick and beam style of construction, including in Toronto and in Vancouver, where I am. It's a pretty common approach to construction using mass timber back in the late 1800s or early 1900s. So this is not new. This is not a new approach. It's just a new way of looking at it. More recently, we have seen a number of tall wood examples throughout the world, and many of these buildings preceded any code changes. So they were paving the way for the research and the testing and the experience needed to eventually lead into those code changes. So where we are today with the code changes are thanks to these precedent buildings, including buildings in Canada, as well as in Europe, and more recently Ascent in the US. So that's all led up to today. The NBC 2020 was a big step forward with mass timber. That was really embracing the EMTC with the 3 different typologies for the 8-story, 12-story, and 18-story buildings, and the different requirements that go along with those. So those have been recently adopted in Ontario, and we'll be diving into the specifics, or Amir will be diving into the specifics of the code, what the code has to say around encapsulated mass timber construction right now.
Yeah, thanks, Ilana. So yeah, as Ilana mentioned, EMTC was a type added in the code, and it stands for encapsulated mass timber construction. And it's, when we look at it in the context of the other construction types, obviously we have non-combustible construction that uses non-combustible materials for the primary structure. Combustible construction, so that's the old heavy timber and also light wood frame construction. And then now we have encapsulated mass timber construction, which achieves a level of safety and fire resistance through the encapsulation of the structural timber elements. And that essentially is that level of safety provided by that makes it different from combustible construction. So even though the materials are themselves combustible, by having that minimum encapsulation, they are providing a higher level of safety. And so this chart provides an overview of all the new groups of occupancy groups that are allowed with EMTC construction. So in the last code round, we only had group C and D permissible, and now it's expanded to the other groups. But today we're focused on Group C in residential construction. And so the new code, as you can see, has 3 tiers in a way in terms of encapsulation. So up to 8 stories, which it previously was limited to 5 and 6, is non-encapsulated with some exceptions, and I'll go through that. And then between 9 and 12 as a 50-minute minimum encapsulation, and then above 12 to 18 is a minimum 70 minutes of encapsulation. And so when we dive in a little bit deeper, so in addition to the encapsulation requirements, the mass timber elements themselves have minimum dimension requirements, which they previously did as well, and that continues. And there's calculation methods to allow for the level of how much timber you are able to expose in a unit. But then if in general, your floors are encapsulated on the top with some kind of cementitious material, on the underside with sheetrock or gypsum board, and similarly with the exterior side of exterior walls, the interior side of walls, and shafts and exits as well. So just as I mentioned in the last slide, these are the minimum dimensions for the timber elements themselves. So for walls, floors, beams, columns, you still do need to follow the minimum dimensions prior to encapsulation. And then in that availability of height where encapsulation is not required for the majority of the members. The exception is that surface spaces, public corridors, exits are still required to have that minimum of 25 minutes of encapsulation. And so what do the minimum requirements of encapsulation translate into in terms of gypsum board? So 25 minutes equals 1 layer of 1/2 inch board. 50 minutes is 2 layers of 1/2 inch, 70 minutes is 2 layers of 5/8, and 80 minutes is 3 layers of 1/2 inch. The encapsulation requirement for the floors is 50 minutes. So that equals 38 millimeters of concrete topping on top of the floors. And then you can also use other non-combustible materials to achieve this. And then on the right here just shows that there are specific requirements to how the gypsum board is installed as well. So lastly, the minimum requirement is prescriptive, and that can contribute towards the fire resistance required for the building, but it is not one and the same. So if you have a minimum, let's say minimum 50-minute encapsulation requirement, but you have a 1 hour or 2 hour fire resistance rating requirement, that gypsum board is contributing towards that, but needs to be looked at in terms of specific tested assemblies to provide the remainder. And then this is where things get a little bit complicated in terms of the amount of exposed surfaces that are permitted. So within a suite or a fire compartment, there is you're allowed up to 35% of the total perimeter wall area to be exposed in the surfaces of the beams, columns, and arches. And then similarly on the walls, again, you have the minimum 50 minutes of encapsulation requirement, unless the walls are more than, you're only exposing one wall as opposed to 2 opposing walls, and those walls are more than 4.5 meters apart. And then similarly with ceilings, the 50-minute requirement, unless it's less than 10% of the ceiling can be exposed. If the flame spread rating is less than 150, and you can bump that up to 25% if the flame spread rating is less than 75. And then there's an aggregate calculation, which you can use different combinations of beams, columns, ceilings, and wall exposure, and that needs to be calculated per case.
Thanks, Amir. I'm going to be talking about the timeline of mass timber projects, because mass timber in tall wood buildings is relatively new to our industry and it's nuanced. I think it's worthwhile chatting pretty in depth about how a tall timber project might be run in the best case, like what we're striving for, what's going to give the best results. So typical project life cycle for any project, not necessarily timber, is you have a design phase where the engineering happens, the design really happens, and then you hand it off to a construction team. And that's where there's still more engineering, there's still more design that happens, but it's typically by a different team. And that handoff in a project material that's common, there's conventional approaches, is usually quite straightforward. Everyone knows what they're getting and what comes next. With mass timber being newer to the industry, though, that handoff can be quite messy if the build phase isn't thought of in depth during the design phase. So if I break that down a little bit more, we've got 4 kind of sub phases. We've got a pre-design or the planning phase. We've got a design phase. We've got production and manufacturing with mass timber. That's where the mass timber is getting produced. And then we've got construction, where the building is being assembled and built. So what that looks like on a mass timber project timeline means there's certain stages. So the white circles with the numbers, those are certain stages where we want to make sure that we're doing what's best for the mass timber project. So that the building can be successful. It can be cost effective, it can be fast, all the reasons that Amir shared earlier on about why we want to build mass timber. Those reasons only really come about if the project is run thoughtfully and efficiently. So we'll go through each of these different stages to consider and try to help understand what's needed here. So we'll start with feasibility and concept development. And the key here is really setting up the mass timber project as a mass timber project, which means front loading some of that design and thought process and some of those considerations earlier in the process. That's really demonstrated here with the McLeamy curve. The essence of this curve is really preempting both the design and the coordination to end up with the most success. So you can have the most influence early on, the least cost of change. You're trying to avoid those costly and time-consuming changes later on when you hand off the project to the construction team. And that's achieved by bringing in the constructability early, bringing in input from the suppliers and installers early. We'll talk about what that means from a design assist standpoint. And that's necessary without the conventional wisdom of decades of mass timber construction behind us. We just don't have that in our industry. So we need to be considering more of that upfront. So these are the considerations that go into that upfront planning for the McLeamy curve. The earlier that all of these are considered and considered in an integrated way, the better for the project. So we're going to be speaking on each of these, and we'll start with the structure. So there's many ways to frame mass timber. There's no one right or wrong way. But there's also ways that are more common than others. So what we're seeing here on this slide is a range of post and beam, point supported CLT with no beam supports. We have beam and purlin. We have different kinds of composite, timber concrete composite, timber and steel beams. We have timber and lightwood frame. There's quite a range of structural gravity framing, and that's not even to mention the lateral system, the cores or the concrete cores or the braces or the mass timber lateral approaches. But today I'll just focus on the gravity system. So the framing we see here can really be summarized by three common approaches we're going to see for a mass timber multifamily residential project. It's going to be slab and beam on the top left. It's going to be point supported CLT on the middle left, and then we have the steel beams with the mass timber slabs. So point supported is one of the more common framing approaches that we see for tall mass timber. The reason being it best mimics a concrete flat slab approach, and it means that finishes and services are extraordinarily easy to coordinate and to apply. Some of the limitations of this system, or the main limitation, is really the column spacing. Because each corner of the CLT has to be supported at a minimum, it means that the columns have to be spaced at the CLT panel width, which is going to be 10 or 12 feet, depending on the supplier. And that means you end up with a sea of columns closer than you might otherwise see for, say, concrete or steel residential construction, more akin to the kind of wall spacing that you would see for the lower rise lightwood frame projects. One of the other limitations of this system is that CLT is really the only option for the floor panels, because it has to be spanning in two directions. We can't use a unidirectional product like NLT or DLT, but it can be very, very cost-effective approach, which is why we've seen buildings use this approach. And for any of these framing types, switching out the glulam columns to steel columns is always an option to further hybridize the design. The next most common approach that we tend to see is a post and beam with a one-way floor panel. The nice thing about this one is the panel spanning one way, so we can use a range of products. We can look at CLT or NLT, DLT, or even GLT, though CLT tends to be the most commonly used, followed up by NLT. This system means that the coordination with the MEP needs to be much more thought through much earlier on to make sure that you're not running ducts through beams or under beams. But because you only have beams in one direction, typically it opens up the door for with some thoughtful pre-planning and coordination, you can avoid that or make sure that the MEP is integrated with a mass timber structure. And then the final approach that I'll talk about is steel frame with timber panels. And quite similar to the post and beam that we just saw, we use a range of different panel products for this system. This steel might allow us to better run some smaller services through and coordinate that. It also might reduce the depth down, open up the column spans a little bit more as well. So some more options there. So here's some photos of some of the various systems that we've seen on our projects or we've used on our projects. Here we have post and beam with CLT panels. And here we have point supported CLT. So you're really trading off the flat slab for the column grid spacing. So point supported CLT just means a much denser grid of columns, but a much easier structure to work with from a coordination standpoint. Now, when we look at volume, volume is one way to look at the cost of what the structure is going to be. It's really only one approach. There's many others. Piece count is another approach. And we'll speak about why only volume isn't or why volume isn't the only consideration. But when we look at volume alone, we see that unsurprising with smaller grids, we reduce volume. So a post and beam 15 by 18 grid is a more efficient structural system than a 15 by 24 post and beam grid. We also see that post-supported CLT lands somewhere in the middle of the post and beam ranges, but it comes with the smallest grid sizes. What it also doesn't have is it doesn't have beams. So there's a cost savings from the fact that beams are higher cost by volume than CLT panels. So the cost of a point supported CLT, even though it might be slightly larger volume, might be quite comparable to a post and beam with, say, a 15 by 18 grid. So as I said, timber volume is part of the cost, not the full cost. The beams and the columns being glulam are going to be much higher in cost to the CLT by volume. So minimizing beams and maximizing CLT is usually a pretty efficient approach to a degree. And piece count also comes into play. Piece count, it especially for how long a project is going to take to be built. Sites are always limited by cranes and crane time, and the more pieces you have, the more crane time you need, and the longer the erection is going to be. Fewer pieces is going to be a faster build. So back to what Amir was saying at the beginning, with one of the reasons to build mass timber is for fast construction, and that has to be considered all throughout the project to actually turn into fast construction. Connection approach and encapsulation also factor into the cost of the project. So what you're seeing here in the image, this is the penthouse of a 12-story mass timber project on the West Coast. The project up until this point was extraordinarily simple, everything aligned, was very, very cost effective. And this feature space, while the volume of wood wasn't enormous, you can imagine by the complexity of the connections and the framing, the cost of the space was super high. One pitfall, one thing to avoid, and we see this again and again, is adapting a concrete scheme or a steel scheme to mass timber without considering the needs of the material is not going to result in the most efficient structure. So we have a project here that's a commercial space, not residential, and it was a concrete scheme adapted to mass timber, and you could see the volume of the components here. It's enormous, and it's not going to be the most efficient way to produce this building, but sometimes the design gets too far down the path trying to design towards a concrete scheme. There's a late change to mass timber, and it's not going to be the most efficient way to set up a mass timber project. You really want to front load making sure the structure is efficient for the mass timber and the architecture is designed around that structure for the mass timber. So next step past the pre-design is selecting a design team and making sure that the design team has experience. This is a huge factor in the success of a project, and it factors into that front loading that we talked about, because that early integration, early planning can only really be done with a team that's experienced with mass timber. If a team or part of a team lacks experience in mass timber and the client's looking for a mass timber project, then it's really important to recognize that and to bring in mass timber experience and expertise, either through a supplier or through an installer, and take a more of an integrated design assist approach to the project to make sure that that early integration can happen when it needs to happen.
Thanks, Ilana. I'm just going to touch on MEP considerations in the design phases as well. So I think similarly to everything else, really the message is, again, to bring some of this thinking up front, to spend some time with your team, thinking through the options and the routing and the systems that are going to be used, because you're using them in conjunction with a different structural system that you may have been used to in the past. And so doing things the same way may not make sense. It may in some instances, like if we're talking about the point supported scheme, you have a lot of flexibility in terms of your routing and distribution, but at the same time, you also don't want to clutter your space with your systems. So again, bringing some of that thinking up front and thinking through it and how that routing and distribution is going to be done, so that it looks the best in the final condition, and is giving you efficient runs as well. And then, working through some of those things in close detail, as you're developing your assemblies and your distribution, and really how they interact and where your concealed spaces are and how you need to protect them, and penetrations as well, thinking through all of those things in unison. And then, if you do a good job and they're successful through, then you'll end up with a result that has minimal impact to the appearance of the final scheme, and is not really invasive in terms of how the systems appear in relation to the exposed timber, if you have it. Next, Ilana is going to touch on fire safety and codes.
Thanks. Yeah, so Amir did a deep dive already into the EMTC code requirements. I wanted to get a little bit deeper into what we mean when we talk about encapsulation versus charring. Charring is a predictable thing that happens to mass timber when it's exposed to heat and fire, unlike, say, light wood frame construction, which would behave very differently in a fire without the encapsulation because there's so much surface area. Mass timber is a much denser product, burns quite predictably and quite slowly. And as it burns, it develops a protective char layer that prevents the rest of the wood from heating up and combusting. So we can use this understanding of how mass timber reacts to fire to design for it. So the gray area you're seeing is the char layer. we assume as a sacrificial layer in, say, a 2-hour fire, and we make sure that the remaining structure after that sacrificial layer is charred and lost is still adequate to support the loads of the building. We make sure the connections are also protected within that space. So what that means is we can mix and match between charring and encapsulation to do what's best for the project and still meet the code requirements. So EMTC has the 2-hour fire ratings, and it gives requirements for minimum encapsulation for the different heights, including the 8-story for residential buildings, which doesn't require encapsulation. But the trade-off that exists for that is you lose more material to char. So you have to oversize the material. So an example here, just schematically, is you may go from a fully encapsulated structure that requires 3-ply CLT and a smaller glulam, or you may want to expose all the CLT and all the glulam, and then you end up with a 5 or a 7-ply panel and a much bigger glulam. So it's a trade-off between volume of wood, exposure of wood, and protection by encapsulation, and of course, meeting the code requirements as well. So the encapsulation does mean covering up the wood. It also means that you can be specifying industrial grade of CLT and glulam, which will come at a bit lower cost than appearance grade. So one of the many trade-offs that we see for these projects.
Next, I'm going to touch on moisture management, and that's predominantly for timber projects during construction. And some of the things to be cognizant of as you're working through the design, and also working with the construction team and preparing a moisture management plan through transport and through construction until the building is finished. So one of the things to be very aware of is that the end grain of timber is the most absorptive, the most vulnerable. That is where the water ingress happens, and needs to, if the timber does not have the ability to dry out, could lead to potential failures. I do want to add that timber is being a natural material from a tree throughout its life is dealing with moisture and is quite good at managing it. It's just that when we put it into a building and have a one-way flow of moisture getting in and not a way for it to get out is when we get into trouble. So one of the other things in the middle here that we're showing is that, so when two panels come together, they're often joined with plywood spline. This can also be a steel spline on top of the panel that doesn't require routing as shown here. But again, that creates another potential area of ingress from the surface that could then lead down to the edges and the end grain, and again, where that's vulnerable, and then that moisture starts to spread throughout the panel. And I'll show on the next slide, one of the ways we deal with that through membranes, but also another way is through surface treatments, such as repellents and coatings that are shown on the right. But that these days is less prevalent unless the member is planned to be an exposed, visual member, architecturally exposed, in which case you would choose that approach. So the most common way of dealing with moisture ingress, particularly on the panels, is to have a breathable membrane applied to the top. And this can be either done in the factory before it arrives on site, or it can be applied once it is in place. And then so that there's rolls that get applied over the majority of the surface, and then the splines are then covered with additional tape to make sure the seams are not vulnerable. I think in terms of these couple of considerations when dealing with these membranes is that understanding your floor assembly and what's going to go over it, because often these are, even though they are considered temporary membranes, they are left in place. And so understanding your assembly and how the layers that will go on top of it will interact and making sure that it's not posing any challenges in that regard. And then some other considerations in terms of moisture management. Other places in the world use that kind of protection shown on the left. That's an image from a project in Sweden. That's not common practice in North America to provide that kind of tenting, but there is a lot of things, a lot of benefits for doing things that way. Not only that it keeps the water out, but also provides very comfortable working conditions for the folks who are working on the building as they go. But again, that's not prevalent in North America, but we'll see if that picks up. And the other major consideration is the building enclosure itself. So the more quickly you can get the building air and water tight by putting your building envelope on, then the less susceptible it is to the environment. And then some other things to keep in mind are where you do have exposed timber on the exterior of the building, managing how that interacts with water. So, for example, on the top right, where there is roof coverage that extends over it, so that wind-driven rain can't get to those elements. Of course, those elements would be coated as I described earlier. And then in the bottom row, let's say the bottom right, lifting the timber off of the ground so that you're preventing pooling water from entering the end grain there. And then when you have overhanging wood that water can sit on, handling that through flashing and drip edges and other means to get, again, not let the water stand and drip and reach the end grain again. And we'll touch on building enclosure as well. So as I mentioned in the last slide, it's one of the key ways of mitigating water as well. Having a building envelope that goes in quickly. And so obviously this leads us to unitized approaches. Everybody familiar with curtain walls, but there are other panelized approaches with cold form steel that could be used that can quickly close up the building as well. And so we see some examples of this here. So on the left, kind of traditional size format, where that could be built of a cold form steel structure, or could be traditional curtain wall. And then on the right, a kind of very large format mega panel has the advantages of enclosing your building even more quickly, but has additional considerations such as the weight of the panel and in conjunction with the crane capabilities and so on. And then lastly, touch on acoustics as another area of consideration as you're going through design. Particularly in residential construction, obviously you'll have your minimum acoustic requirements, and you'll also want to mitigating transfer of sound between units, both through your floors and ceilings, as well as through your partition walls. And so, this is another area to work closely with your consulting team to really understand how your panel layouts are interacting with your demising scheme, because often you'll want panels not to span over demising walls from one suite to another that will bring flanking noises and vibration through the panel that can be mitigated through various means, through isolation products, through soffits and other things. But you'll want to work through these early on. You don't want any last minute surprises.
Amir. Now we'll go to design assist, choosing a design assist partner, what design assist is, really try to clarify. I think one of the least understood parts of mass timber projects is how design assist works and what it's for. So if we start from the fundamentals, we need to consider material and methodology together to really truly get an integrated system approach to any kind of construction. But with mass timber in particular, because again, we don't have the decades of experience behind us, we can't just treat it like any other established material. And it's not just about the material, it's also about how it's built. So that's how we get to the successful system is considering both in tandem. We think of design as a linear process. Something gets designed, it gets given to the contractor and it gets built. We know that that's not truly the case. Design is much more cyclical with some phases of redesign and coordination happening in that cycle before a project gets built, especially in the BIM world or in the virtual model world. So the specifics with mass timber now adding to this already not linear process is we have to consider the fabrication and logistics requirements. Every supplier, every installer is going to have a different approach. Suppliers might be local, they might be anywhere in North America, they might be in Europe, they might be elsewhere. So travel logistics matters and transportation. All of that has to be factored into the design and the planning. So what we end up with is a model that now has these additional inputs needed from manufacturing, from the installer, to get a properly designed and coordinated building system. Now, that can be helped with having a higher level of virtual coordination. Having a digital twin can really help that coordination process, and we'll talk about that a little bit later in fabrication design.
I'll touch on a little bit what the scheduling impacts of design assist approaches may be in relation to a traditional design bid build approach, which we see here. Often what can happen in a traditional design bid build approach with a mass timber project is that once it goes to bid, if there hasn't been supplier input prior to that, once it gets into the hands of the suppliers and they look at it through their lens of their specific products and their specific fabrication capabilities, they'll want to make suggestions to make the design more efficient and more suitable for their production means. And so what often happens is that they'll provide that input at that point, and then an owner will be like, well, I don't want to leave that money on the table. I would like to take advantage of those potential efficiencies that will lead to savings. And so that will initiate a redesign. But this has the impact of extending the schedule and the design team being re-engaged and the potential impact to additional services in that regard, and then ultimately will extend the entire schedule as well. So the approach that we often recommend is that overlaying that input from suppliers, installers through the design phases through a design assist, and doing that through the latter half of design. And that coordination and that knowledge and that information gets incorporated into the final design and leads to a more seamless process in terms of the execution of the delegated design work that happens from the suppliers, and then ultimately towards construction. And so what does that look like in a more fine grain? It may mean if the ultimate goal is to have some portion of your design phase, your construction document phase, devoted to design assist, where that input is being provided. It means really starting this process much earlier on. So at the latest, starting your procurement model at the beginning of construction documents, and that is a model that has all the timber components, the superstructure, has indications of where the M&E openings are, and the geometry is more or less fixed. Like you're accounting for all the components and all the elements, and and your understanding of the loads that will be imposed on them. And then from that model, engaging the trades and going through a selection process, and landing on a design assist partner that can be with you for at least the latter half of construction documents. This could be moved up if the team is in really good shape, and starts the really front loads the coordination process. It is absolutely beneficial to move this even further ahead in terms of the design schedule. And then so as I was saying previously, so the delegated design work that we have labeled here as detailed member and connection design can also begin rather than waiting till much later on. And so that can lead to the materials arriving on site much more quickly. And so if there is a need, if there's a condensed schedule and material, the superstructure needs to arrive on site a few, 3 months, 4 months after the closing of the construction documents phase, this approach would allow that. Otherwise, you're looking at 4 or 6 months at least beyond that if you're starting the process after construction documents.
Okay, so what is a design assist partner and who can it be? Design assist partner can be a range of things. A general contractor can be a design assist partner, a supplier or fabricator can be one, or an installer. The key that unites all of these is they must have mass timber experience. Pulling, say, a GC as a design assist partner onto a project with no mass timber experience is not going to provide the industry expertise that you need in a design assist partner. What a partner might do, it ranges. It can be some or any of these things. It can support, a design assist partner can support with procurement. They can provide specialty engineering, or they can hire an engineer to do the specialty engineering. They can help with construction scheduling. They can help with constructability. They can manage the complexities of an international supply chain. They can manage and run the delegated design. They can guide the design for efficiency, so cost efficiency and structural efficiency. They can reach out to a range of suppliers and get early pricing, or they can sometimes do turnkey design, supply, and install. So it's a pretty huge range. They could have a minimal input onto a project, or they could essentially do the entire mass timber portion of the project from design through construction. So we've talked a lot about some of the reasons why you might want to bring a design assist partner on board. Some of the most common ones are to inform and guide the project so that it's efficient and constructible. You'd bring them on board to provide specialized knowledge about cost, shipping, supply, and constructability that the team otherwise wouldn't have access to. Sometimes they're brought on board to provide access to international supply chains. And they can be valuable, especially for unique or unusual projects. And today, in a newer market for tall mass timber, most tall mass timber projects will fit that category. And design assist partner is not always going to be necessary, though. If the team is experienced in an established market, it may not be beneficial to the project. one of the common questions we get is, how do you stay competitive with Design Assist? And there are a few options. One option is an early tender of mass timber. So what Amir was showing with that timeline is at 50% construction documents say you bring a Design Assist partner on board. That partner could be a supplier, and it could be through an early tender of the mass timber. So all of the suppliers have a chance to bid, and you can make sure you're getting a competitive price. Another option to stay competitive is to engage a GC or an installer as the Design Assist partner, not commit to a supplier install price upfront, so that you could stay open further along the design to supplier options. And then that GC or installer is bringing in the expertise necessary to make sure the design is still efficient for mass timber, it's still constructible, it's going to work for a variety of mass timber suppliers. And some things to be aware of and to be cautious about, or just to have on your radar even, is that a Design Assist partner is probably going to be biased towards their own capabilities. So obviously a mass timber supplier brought on board as a Design Assist partner is going to want their product to be used in the project. The other key to look out for is asking for a hard supply and install quote too early in the project with minimal building information can be problematic. We've seen projects go out for a Design Assist partner where the project team is looking for the Design Assist entity to finish the design and do the full supply and construction of the project and give a hard cost. And the project was at like 50% SD. So project is very, very early. There's minimal design information to use to bid. There's minimal mass timber information to use to bid. And the Design Assist partner is being asked to provide a hard cost. That's never going to be efficient. Suppliers and installers and GCs are going to pad their numbers enormously and caveat everything to make sure that they're protected while the design gets complete and is going to be changed. But in contrast to that, starting Design Assist as early as possible is still beneficial, and you can do it without a hard quote. So specialty engineering, that's also somewhat understood in the industry, but not perfectly understood what is specialty engineering and delegated design. So first of all, why do we delegate mass timber design or mass timber connection design? And the answer is mass timber detailing is complex and it can be very supplier specific. Some suppliers have their preferences, some suppliers can fabricate steel for connections, and some suppliers want to use pre-engineered connections that can just be installed in their shop. So because it's supplier dependent, an engineer can't necessarily design all the detailing without a supplier coming on board to provide some input into what's going to be efficient for them. So the cost of delegated design of connections is typically carried by the supplier, so it doesn't show up in the EOR's fees. And that's another reason why delegate, because our industry isn't used to that cost being part of the base design cost from a structural engineer. It's hard to compete on structural engineering fees with that cost carried under the basic design fee. But it's not the right answer for all projects. Bringing the connection engineering in-house can avoid some late-stage impacts to member sizing. Member sizes sometimes are, especially for 2-hour fire, they can be driven by the connection approach, the specialty engineering. And not delegating means that the design team can have a better opportunity to coordinate. So the architect and the engineer can work closest together for what's going to work for the design of these potentially exposed mass timber connections. It can also lead to a more cohesive system, thought through, where the connection is part of a system. It's not just a standalone element. So what's included in delegated specialty engineering, it's connection detailing is always included. Sometimes that extends to the diaphragm detailing. Sometimes it includes submitting alternate solutions to the AHJ. Sometimes it can be vibration performance. Sometimes even member design, the full structural design is delegated, but that's not as common. And often under the installer's scope is the temporary stability and rigging of mass timber. We've talked a lot about fire. We haven't talked a lot about fire and the impact on connections. Typically when we encapsulate and we assume there's still some char to the wood, that means that we have to bring the connection within that char later. So that connection, which is usually steel or aluminum and is going to be very susceptible to heat, needs to not get hot. Maybe 10 years ago, we didn't see this, but we're seeing this on most projects now, is the addition of an intumescent strip shown here, which means if we get a little bit of shrinkage or a little bit of opening up at the connection, that intumescent strip, if exposed to heat, is going to expand and it's going to make sure that that connection doesn't heat up and that connection, the integrity of that connection stays, and the overall structural integrity is intact. And connection design is more than just the structural capacity. It also has to consider how everything comes together. I think connections can have one of the biggest impacts on construction speed. And as we've said again and again, construction speed really matters for getting these buildings up quickly and realizing a cost savings for time on site. So a connection like this, where the connection helps speed along construction, it doesn't hinder construction in any way, is critical.
Thanks, Ilana. I'm just going to touch on 3D fabrication modeling a little bit, which is kind of the last phase before we go into actual production of the components. And so, yeah, this is typically done by the supplier, but similarly to specialty engineering, which can be delegated, if the structural engineering team has the capabilities to do this work, it could sometimes fall in their court as well. And what it really is the finalization of the design down to the screws, and the specific screws, the specific patterns of those installation requirements, the sequencing of the installation, and all the final tolerances in order for the components to be able to be assembled in the manner that they're intended. It may also involve sequencing plans for how the materials are packaged and the logistics as well. And it's absolutely critical that this happen because it is essentially like the shop drawings that you would have in any other process, and there often is traditional shop drawings that accompany a fabrication model that are reviewed and approved by the design team, but it also is that model is done in a specific software platform that allows the supplier to send those files directly to their fabrication machinery on the shop floor. And it is a final QA/QC check as well, and puts the burden of responsibility on the supplier for ensuring that everything is done correctly. And then lastly on fabrication. So yeah, I touched on the machinery. So those fabrication models communicate to CNC machines like this that have multiple heads on them. We're seeing a saw blade on this one, but they have routing capabilities and other things to be able to create various profiles and pockets and drill holes and all the things required for the timber connections. And as I mentioned, we've touched on before, where your material is coming from and where that supplier is located. Not only are the capabilities of their fabrication facility go into consideration in your design, but if you're shipping overseas and your material has to go on a ship versus going on a truck or going on a train, each one of those things will have a slightly different impact and restrictions on the size and weights of the components. And your design will need to be geared towards that specific supply chain. One of the final things to consider is how your material arrives on site. Is it coming just in time to be picked and erected, or is it coming a little earlier so that you have a backlog of materials sitting and waiting for the erector to have that flexibility, and if that's the case, making sure that staging areas are available or temporary storage facilities off-site that are within close distance to the site where materials can be picked up from those in-between facilities and brought to site in a short order. And I'll hand it over to Ilana to wrap up the timeline.
Yeah, and then it all comes together with the install. So this is where working with an experienced installer is super important. You can bring in design assist expertise everywhere else on the project, but the people installing it need to have worked with mass timber before, especially for these taller or bigger mass timber projects. Stability during construction is often overlooked at the design stage. So we make decisions like, say, using timber concrete composite that requires a bunch of additional temporary shoring. And that doesn't usually get priced, or that doesn't usually get considered for how that might slow down construction or what the construction sequencing might need to be for that sort of type of construction. So this comes into play with hybrid structures. This comes into play with even when and how concrete topping gets poured for diaphragms. But it often gets missed up until the installer is pricing it, and it could make the difference of hundreds of thousands of dollars in install costs that has nothing to do with mass timber volume. So one example of this is we see concrete diaphragms used as a structural concrete layer on the mass timber where the concrete topping is structural. We see this sometimes less and less, but when it's the diaphragm, it's the tie for tying all the panels into the lateral system. So we don't have stability until we have that concrete topping in place. But concrete topping is almost always poured after the structure is entirely complete, after the wood structure is entirely complete. So that means that the wood structure goes up without any tie, and an erection engineer hired by the installer has to come in and design workarounds for this, to tie in the CLT to the lateral system. And these workarounds can be quite extensive sometimes. So this is a good example of where foresight and forethought in constructability can really play into the design of a mass timber structure to keep it efficient from all directions. As Amir mentioned earlier, getting the envelope on as a critical path item is going to help keep the wood as dry as possible. What's shown here, these are Cree panels. These actually have structure as part of the envelope, so you have no choice but to install these panels as each level goes up because it supports the level above. So that's great because it forces the envelope on, but regardless, like if this approach isn't taken, you still want to make sure that when and how the envelope gets applied is thought about early on and definitely discussed with the GC or the installer.
We'll quickly wrap up with a few takeaways, and we'll move on to questions if there are any. Again, reiterating that it's critical to move a lot of that coordination and thinking earlier on in the design phase. so that you can reach the constructability measures that you're aiming for and the scheduling measures that you're aiming for in time, when you have the ability to influence change in design and things aren't locked in, and people aren't tied into to certain approaches. Water mitigation on site, and this goes to a lot of various things, but as shown here, the members that are sitting on the deck are raised so that they're not sitting in potential pooling water. The temporary membrane is on there, the spline tape is on there, and people will be manually managing water as well through squeegeeing and various means. Here's some more examples of critical areas where water could pool are protected. Obviously, the splines and joints as well. As we touched on before, not adapting a design late in the game from one system approach to mass timber, but really approaching the project and designing for mass timber from the get-go. And then thinking through all your detailing and your considerations in a way that you can capitalize on the speed of erection potential of working with mass timber so that it can become competitive with other approaches. We'll wrap with that. Thank you all for listening.
Great, thank you so much. I think we have one question that Ashley's going to ask, and then in the meantime, we still have 13 minutes. So if there are any other questions, just a reminder for those on the call that you can enter those questions in the Q&A by just clicking on the Q&A button, then you can type them. But we'll just start with one question.
Okay, so what do you think the impact of the new building code changes will be on the market for tall timber residential? And that's to both of you, if you want to take it.
Sure, I'll start. Over the past couple of years, we've been working on EMTC projects up to that 12-story limit. And then in the latter half of last year, we're already seeing interest, anticipating the increase to 18 stories, where folks were, some of those projects that were designed originally as 12 stories were going back and getting reconsidered to go taller. And then as we are now in the new code cycle, we're the new ones that are coming forward are definitely going over 12. So they're falling within that 12 to 18 story range. So we are seeing interest there. Of course, the code changes aren't the only thing that influence market trends. So we'll see how things play out. The residential sector, we're also seeing move more towards purpose-built rentals, and the ability of these mass timber projects to be built more quickly and get moved into and occupied more quickly is also being taken into consideration from the projects that we're seeing come across our desk.
Yeah, and I'll just add to that, that it's interesting because we saw the dawn of mass timber construction in Canada really start on the West Coast, and that energy is really moving to the Ontario markets. On the West Coast, we're seeing much more interest in tall mass timber student housing, but less of the same level of interest in multi-unit residential that we're seeing in Toronto. So we'll see what the impacts down the road of the code changes are. But like Amir said, it's not pure code. There's other factors that come into it as well.
Okay, I have another question for you guys. Can you both name and describe a tall timber residential project in Canada that you both find inspiring right now?
Yeah, I'll start there. We have several on the boards right now in the GTA that are tackling the need for higher density, sustainably built, purpose-built, affordable residential. And so for us, like having projects that really are aiming to tackle all of those challenges is really great, and is inspiring for us. And to see that it's not, in the decade that's passed, you'd get one of those projects every once in a while, and now it looks like there's real momentum in trying to do that much more consistently, as a fundamental approach, not a novel approach.
Yeah, I'll speak on, I think one of the most inspiring projects for me was my first mass timber project. That was Tallwood 1 on the West Coast, on Vancouver Island. So that was a wonderful learning opportunity for me, and pretty inspiring to see a mass timber project like that go up.
We have a question in the Q&A. One of the attendees is asking, how did we get started or get the opportunity to work on mass timber projects? I can start, and Ilana can say it. So I was working as an architect in New York, and the U.S. Department of Agriculture, which oversees forestry in America, this is a decade ago now, was seeing the advancements of mass timber construction elsewhere in the world, predominantly Europe, and wanted to increase the opportunity for that type of construction in the U.S. And they held a competition. Canada had done the same thing a couple of years before that. And these were to result in demonstration projects which could take on a lot of the code obstacles, and help the kind of learning curve in utilizing materials that were unfamiliar in this market, and learning how to design with them. And so I was lucky enough to have the opportunity to work on that competition, which led to a grant award, and a lot of R&D that followed, and I've kind of stuck with it since.
Thanks, Amir. I'll share mine. I think the question, though, is interesting because a lot of what we talked about is how you need to make sure you have experienced people on the projects, and everyone needs to learn somewhere. So I don't think it's hopeless for people without mass timber experience. I just think it's key that you bring in mass timber experience to the team to be able to learn from. My mass timber portion of my career started after about 5 years into my design career, I paused engineering to do a master's, really with a goal of learning about mass timber and starting to get integrated into the mass timber world a little bit. And I met some great contacts. I got to work on some great research projects and break some CLT panels. And out of that, I was able to really kind of dive into some mass timber projects from an engineering standpoint and get my hands wet on projects starting much smaller than these Tallwood projects, but learn and grow from there.
Great. I think we are just about time, and I don't see any other questions, so we will wrap up. Thank you so much, Ilana and Amir. That was a great webinar. Really, really lots of information and a good discussion. So thank you so much, and thank you for those who attended today.